Hi students, in this series of videos we will be trying to summarize the important aspects related to organic chemistry. You know that in J main and also in J advanced the nature of organic questions is something unique in the sense that questions are always mixed concept based, right? So they are logical also and all are understanding based. Nearly all questions from organic chemistry are understanding based. Only sometimes a few 1 or 2% questions will be memory based. So you know that there are a lot of reactions, near 300-400 reactions if you look into the organic chemistry branch as per our syllabus, and it is very difficult to learn them individually, like in every case. If we have more number of something, then it will be very difficult to individually analyze them, right? So what we can do is that we should be doing a systematic categorization of the reactions. Then only our studies or our performance will be improving. Okay. So having that in mind, here we are trying to categorize the whole organic chemistry branch into certain viable branches, viable subtopics or categories. And the first one being the simplest of all, the addition reactions. So first we will be looking into addition reactions, the important one, the frequently asked ones and the more relevant ones from all chapters of organic chemistry. You know that addition reactions are common for compounds containing pi bonds, right? Pi bonds. And elimination reaction is just opposite of that. Elimination reactions are ways to prepare pi bonds, right? Preparation of alkenes, alkynes, etc. We do elimination reactions. So they are like mutually opposite of each other. The addition reactions therefore are very common as per our syllabus. They are very common in 4 different categories of compounds, that are alkenes, alkynes, where we have CC pi bonds, and then aldehydes, ketones, where we have CO pi bonds. Their addition reactions are very common. It is their usual reaction. Okay, and you know that there are different types of addition reactions according to mechanism. And these are electrophilic addition, free radical addition, and nucleophilic addition reactions, where the electrophilic and free radical additions are the usual ones for alkenes and alkynes. Therefore, we will be learning them separately. We will look into, we'll be taking here the alkenes, alkynes cases in the first session of this series. And later we will be seeing the addition reactions of aldehydes and ketones, which are the so-called nucleophilic addition reactions. Okay, here we will be seeing mainly the electrophilic or free radical addition reactions, which are characteristic of alkenes and alkynes. Okay, so let's move into the topic, electrophilic or generally addition reactions of alkenes and alkynes. So let's first think about the alkene-alkyne substrates. They are generally electron rich, right? They have C, C and H present in them, and the CC pi bonds are therefore kind of electron rich only, and it is for this reason that first the electrophilic part, or if we are trying to add a molecule AB, let's say it containing A plus and B minus parts in the adding molecule AB. It is first A plus which goes to the, or which adds to the alkenes or alkynes, because alkenes and alkynes are electron richer. Okay, so first electrophilic part adds in the first step, let's say, and later the nucleophilic part adds, B minus later adds. Okay, so that is a sequence. There is a sequential addition in most of the cases, except in few cases like hydrogenation reaction or hydroboration reaction. There the addition is simultaneous. Okay. Other than that, if you look into the addition reactions of alkenes and alkynes, they are like electrophilic addition reactions. First, the positive part adds. If you are trying to add a halogen molecule, first halonium forms, right? First X plus, Cl plus adds, Br plus adds. If you are trying to add H2O on an alkene or alkyne, first the H plus adds, later only OH minus comes. If you are trying to add first, let's say HX molecule, hydrogen halide, then the H plus adds first, then only the later session only halide ion interacts with the alkene. So there is a sequential way in which this functional group or the substrate behaves towards the addition molecules. Okay, so before going into previous questions, let's first look into the details, a few important aspects of these reactions. If you have forgot it, let's brush it up first and then look into the previous questions from this category. Okay, so while talking about addition reactions of alkenes, the main reactions under this section are addition of halogen molecules. If we try to react halogen molecules with alkenes, what happens? And here we have three different options. We may add halogen molecule using CCl4 solvent, or let's say CH chloroform solvent, some non-nucleophilic or non-reactive solvents. And other option is we can use aqueous medium for this reaction. We can do this reaction, we can treat alkene with a halogen in aqueous medium, or other is alcohol medium. These are the three main categories, and you can see the difference in the products also. If you do addition of halogen in CCl4 solvent, we will be getting vicinal dihalides. Vicinal dihalides will be the product. And if you are trying to add X2 in H2O medium, we will be getting the so-called halohydrins. So you know that we are now going through the syllabus of this section, addition reactions. These are the syllabus. We are just looking into the syllabus, trying to summarize the reaction first, then let's apply the logics. Okay, if we do the reaction in alcohol solvent, we will be getting something called as haloether. So there's a difference in the products with the change in solvent, and you can see that the change is due to the nature of the solvent. You can see that this is a non-reactive solvent, this is a non-nucleophilic solvent, but these are nucleophilic solvent. H2O is a nucleophile as well. ROH, due to the lone pair on oxygen atom, these are nucleophilic in nature. They are solvents, but reacting solvents also. Okay, so that is the addition using halogen molecule in three different ways. And next we have addition of hydrogen halides. Addition of hydrogen halides, here we can use two different strategies. Addition of HX means HCl, HBr, HI in absence of peroxides. Or we can use HBr addition in the presence of a peroxide. And both way we will be getting haloalkenes, right? We will be getting haloalkenes. Haloalkenes, chloroalkene, bromoalkene or iodoalkane. Here specifically we are getting bromoalkanes. Bromoalkanes. And you may remember that this is a free radical addition reaction. This is a free radical addition reaction. Perhaps this is the only free radical addition which we learned for alkenes. The peroxide effect or Karash effect, there are several names. We call this one particular reaction. Okay, that is the second category of addition reaction. And next we have very important addition of water also. Addition of water. This also can be done in three different ways. we may do addition of H2O using dilute H2SO4, or simply we can write H3O plus for that reason. And otherwise, two options are also there. One is hydroboration oxidation, the reagent you know B2H6, then hydrogen peroxide in NaOH medium, and this is called hydroboration oxidation, we know. And other option is oxymercuration demercuration, HgOAC twice, using H2O solvent, and then demercuration using sodium borohydride. Okay, these are the three ways in which we can add H2O on an alkene, and the product in all case will be alcohol. Okay, these are alcohol products. But there may be differences in the obtained alcohol depending on the mechanism of the reaction. Anyway, if we add H2O on alkene, we will be getting at the end alcohols only. And here we may remember one variant of the last reaction. If we are doing the reaction, this is not addition of H2O then. If we are doing the last reaction, Hg mercuric acetate in alcohol medium, alcohol solvent, and then adding NaBH4. This is now called alkoxymercuration demercuration. Alkoxymercuration demercuration. That was oxymercuration, then demercuration. This is alkoxymercuration and then demercuration. And this will give us ethers as the product. This will give us ethers as the product. Okay. So that is another one option, that is addition of alcohol then. This is addition of alcohol then H and OR addition. This is H and OH addition. Okay. So that is a related one. And now these are the important reactions which fall into addition reactions of alkenes category. Okay. So now let's look into the mechanism. There are some relations also between the mechanism as well. So now let's see what is the general mechanism for each of these conversion. Mechanisms are very important. That is why frequently the questions are asked from these few reactions. Okay, if you look into the last few years, last maybe 11 years questions, then you will see that exactly such reactions have been asked 20 times. Okay, and you know organic reactions are generally mixed type, and if you look into mixing type questions, then more number of questions will be there which applies these logics. Okay, and as such these reactions are directly asked at least 20 times in last 11 years. So you can know the importance of this branch of reactions. That is why we are discussing this simple reaction first of all. Okay, now let's see mechanism one by one. They are very related mechanisms. Of course, we will not be able to discuss everything in detail in this one session, and you already know the mechanism. Just we are doing a recap of the already known mechanisms. Just let's look into few important aspects in the mechanistic pathway of these reactions. First of all, addition of X2. Let's see. Let's take an alkene or C double bond CH2, and if you are applying X2 and X2, you can note over there X2 means chlorine or bromine. Chlorine, bromine, these are the targets. Yes, if you are applying X2, you know that this is electron rich. Therefore, it will be interacting with the positive part of the electron deficient part of the adding molecule, which is X plus. So, first of all, X plus from X2 interacts with the alkene and result in a structure like this. This is called cyclic halonium intermediate, very characteristic. Cyclic halonium intermediate. So due to this particular intermediate, there are no rearrangements observed in these reactions. No rearrangements. Very important. There are some additional reactions in which rearrangements are very usual, and some reactions in which there are no rearrangements at all. So this is one such reactions in which we will not see any rearrangements. So if first group adds on this carbon, second group will be coming on the next carbon only. Okay, these are adjacent or 1-2 addition like reactions. Okay, anyway, cyclic halonium is formed. Cyclic halonium, the benefit of forming such a intermediate is that now octet is complete for all the atoms in this structure. Therefore, it is very stable. Octet is complete for this carbon, this halogen also. Therefore, this is very stable system compared to a carbocation. That is why if such a possibility is there, this will automatically form, and this locks the carbocation. Therefore, there are no rearrangement. You know, carbocations have the tendency to rearrange, and this tendency is reduced in this structure because of the locking with the halonium ion, cyclic halonium formation. Yes, cyclic halonium intermediate forms. This is the first occurring step, and later the later step is decided by the reagent that we use in this reaction. Okay, we can add halogen in this medium, that medium. 3 different medias are there. If we are adding a halogen in CCl4 solvent, then CCl4 will not come on this or will not interact with this because that is non-reactive. CCl4 is non-reactive. If we are using CCl4 solvent, then it is the halide ion which interacts in the next step. Okay, and you know that if halide ion interacts, what happens? If halide ion attacks on this carbon, this or that carbon, doesn't matter, then you know we get a vicinal dihalide or CH2 and X over here, the new X on the other carbon, which is now a vicinal dihalide. That is the case if we are using such a non-reactive solvent. It could be CCl4, it could be CHCl3, it could be any non-reacting solvents. Then addition of halogen occurs. This is addition of halogen only. Now if we are using H2O for the reaction, if the reaction is carried out in H2O solvent, in other words, if we are using bromine water or chlorine water reagent, then what happens is that in the second step, H2O attacks. H2 is a nucleophilic solvent. So nucleophile H2O attacks on this intermediate and it forms corresponding compound which is called halohydrin. We get RCHCH2 OH on this side because H2 attacked there, and X on the other side. This is called a halohydride. It could be a chlorohydrin or bromohydrin. If you are using bromine water, then you will get bromine here, OH here, that is bromohydrin, and otherwise chlorohydrin. Generally halohydrin is the common name. So we got halohydrin, and then if we are using ROH as the solvent, let's say methanol or ethanol, ROH is also nucleophilic. This is also nucleophilic, and this is going to attack on the carbon, and we will be getting RCH2 OR over here and X over there. This is called halo ether. There is a halogen and here is a new ether produced. That is called halo ether. Okay. So these are the possibilities, And you can see that since there is a cyclic halonym intermediate formation, this addition will be anti-addition. Okay, if X is above, OH will be below. If X is above, OR will be below. And there is no competition in this case. Therefore, if one X is above, other X is below. That's it. If one X is above, other X is below. So that way, since there is a cyclic halonym intermediate formation, therefore this is anti-addition reactions. These are anti-addition reactions. Okay, and you may have noted one important aspect occurring in the second step, that H2O attacks on this carbon only, alcohol attacks on this carbon only mainly. Okay, so you can note that point. H2O or ROH attacks on more substituted carbon of the cyclic halonym intermediate Therefore, we can say these are Markovnikov addition reactions. So, this is an addition of HIX. You can call this reaction in that way also. Bromine water means HOX addition, where the OH minus adds on the more substituted carbon, X plus adds on the less substituted carbon, that is Markovnikov addition. Here is an ROX addition, OR minus adds on this carbon, X plus adds on that carbon, if you go through the mechanistic pathway, right. So, these are the halogen addition possibilities. Depending on the solvent, products may vary, but the logics remains the same. And the last point that we have discussed, H2O or ROH attacks on more substituted carbon. So, you can understand that point this way. Let us see once again the cyclic halonym intermediate. This is the structure, right. And here you can imagine like this. Let us say this cycle opens, okay. This is not actually opening. Even if it is opening, then also it quickly reverts to the cyclized structure, okay. Let us assume that it is opening for a short time. Then this is one possibility, R, C, H, positive on this carbon, C, H, X on that carbon. Or other possibility is that this ring can open from that side also, right. These are the two options. If the ring opens from that side, then we will be getting a structure like this, RCH, X, CH2 plus. So, these are the two ways in which the cyclic halonym can be broken, and you can easily find that this is the more stable one, right. This is the more stable cation. Therefore, whenever H2O or ROH tries to attack on this intermediate, it will find more of positive charge on this carbon only due to this fact, okay. Therefore, H2O mainly goes to this carbon where positive charge is more stabilized, and ROH also sees a greater fraction of positive charge on this carbon only. Therefore, OH or OR group attached on this carbon and halogen is attached on that if we analyze the final product, the major product, okay. So, that way this completes the main aspects of halogen addition in three different circumstances, okay. Now, let us quickly go through the HX addition, which is our second. We discussed this. Now, let us see this thing. and addition of HX, very simple. Addition of HX, let's take the same alkene. Once again, let's try to add HX. You know alkenes electron rich, therefore it is positive part of the adding molecule which interacts first with the alkene. And we get R, C, H, single bond C, H2. H plus goes to this carbon mainly because we are going to get a carbocation intermediate here. No cyclic structures possible here. Cyclic structures were possible in the previous case because it was halogen plus which had a lot of lone pairs present on it, right? So it could act as a bridging group due to presence of lone pairs, multiple lone pairs. But here it's not the case. Here it has to happen that a carbocation has to form as such. Carbocation intermediate. Therefore, you can imagine the later cases. It may rearrange. Okay? It may rearrange. So, in addition reaction of HX, there is a possibility of rearrangement. It was not present in the previous halogen addition. Carbocation intermediate forms. All the properties of carbocations you can apply in this reaction. So, you can say it is this carbocation that is formed mainly because this is more stable. If H plus is added on this carbon, then that carbocation is formed which is a primary carbocation. That is less stable, but therefore that does not form in greater amounts. It is only the more stable intermediate. You know that intermediates are products of first or intermediate steps, right? Products has to be more stable. So, it is a product of first step. So, if it is more stable, then only it forms, right? So, more stable carbocation which is secondary in this case will form in greater amounts, and if the secondary has an option to rearrange according to structure, that will happen also. Okay, so this carbocation intermediate is formed in the first step. Now what can happen? Now X minus can simply add on this cation. X minus is a very strong nucleophile, you know. So this happens. C H X adds, and that is now a halo alkane. Halo alkane. So the principle was that first H plus add, we will get a carbocation. So you need to look into all the basic aspects of the carbocation so formed, and later then decide where X minus has to go. There is no such stereochemical relationship between the H and X. If H is above, X can be above or below, because there is a carbocation. It is a planar structure, so X minus can either attack from above or from below. But in the previous case where we saw cyclic halonium formation, there all the time X minus or H2O or ROH has to come from the below side only if X plus was above, or above side only if X plus was formed below. Okay, so there was always a anti-addition happening, anti-addition product formation in this reaction due to the cyclic intermediate involvement. Here there are no such relationships, no stereochemical relationships between H and X addition. Okay, so this is the normal HX addition. X could be Cl, Br or I. Every time the principles remains the same. Now, other thing is that if we are adding HBr in the presence of peroxide, then it is a free radical addition. If we are adding HBr in the presence of a peroxide, HBr, if we simply add, this happens. If we are adding HBr in the presence of a peroxide, then you know that in the initiation steps, from their interaction, we will be getting bromine radicals. That was the so-called initiation. Okay, they interact together and give us bromine radicals, and it is the bromine radical which now adds to the alkene. Okay, it is not H plus, it is not Br minus, it is not H dot, it is Br dot which adds to the alkene first in this case. Okay, it is Br dot which adds to the alkene first in this reaction. Therefore, you can see that it gives us a free radical intermediate, right? This is now Br dot has two options. Br dot can either go to this carbon, creating a radical over there, or go to that carbon like this and creating a radical on this side. This is now a secondary free radical. If bromine goes here, that is a primary free radical. More stable free radical intermediate will be formed because this is a product of the first step. Product has to be more stable. Free radical intermediate forms. More stable free radical intermediate will be formed in greater amounts. Therefore, that leads to major product. And other thing related to free radical is that no rearrangements. Free radicals generally do not rearrange. Rearrangements for our level is very common on carbocations only, not on such radicals or anions. Okay, not rearrange. So no rearrangement in this reaction also. Rearrangement till now we are discussing 5 reactions. Out of 5 reactions, only this reaction has a possibility of rearrangement. Okay. And here, next what has to happen? Next, H has to come on this. Br came first. Now H comes. And HBr from another HBr, one H dot is coming to this carbon. And we get a haloalkane again, which is now a bromoalkane specifically. We cannot get a chloroalkane or iodoalkane directly like this. They do not show peroxide effect due to 2 different reasons which you know. Okay. Here also no such stereochemical relationship. If Br is above, H could be below or above in the second step. Okay. So this is the product, and we got a bromoalkane specifically. This is not electrophilic addition. This is just a free radical addition. That is why initially either H plus H dot or Br dot can add, and according to mechanism it is Br dot adding first. Okay, Br dot is adding first. So that was the second category of reaction for us. And now we have one more addition reaction mentioned in the initial page, that is addition of H2O. Let's quickly see the mechanism of that also. Addition of H2O. Addition of H2O, 3 different ways we can do. One is using dilute H2SO4. Dilute H2SO4. We cannot use HCl or HBr or HI here because then it will be like haloalkane formation or so something like that, because Cl minus, Br minus and I minus are strong nucleophiles. Here you know that sulfate is not a good nucleophile. Sulfate addition or H2SO4 addition occurs only if we are using concentrate H2SO4 at low temperatures, right? Concentrate H2SO4 if we apply, then H plus and HSO4 minus addition occurs. We get alkyl bisulfate. That is not very important reaction. We are focusing on the important reactions of the syllabus and which are frequently asked for long years. Such reactions only we are taking here. Okay, now dilute H2SO4 we are taking. And in the medium, you know, there is H plus, there is H2O, there is sulfate. Sulfate in the sense HSO4 minus. HSO4 minus is there, H plus is there, and H2O is there. Who interacts first? H plus interacts first. That is the electron deficient species. H plus from H2SO4 interacts first. So this is similar to HX addition. First a carbocation intermediate forms, which is a product of first step. So it has to be more stable, then only it forms in greater amounts. H plus adds first in this way because this is more stable carbocation. Okay, carbocation intermediate is present, so rearrangement is present in this reaction also. This is a second reaction in which rearrangement is possible. It may rearrange. Rearrangement means hydride shift, alkyl shift or ring expansion. That is a common ways of rearrangements. Okay, this is a secondary. If there is a possibility of tertiary formation, that will occur. That is a feature of carbocations. Carbocation intermediate formed first, then it is, let's say it is stabilizing by some mechanism, and later who adds? We have in medium H2O in large amount. H2O in large amount because it is a solvent also, and HSO4 minus also. So better one is H2O nucleophile. H2O nucleophile adds. We get OH over here. So if you are showing the complete reaction mechanism, then we will be getting an OH2 plus over here, and the next step, next elementary step, H plus has to be removed, and there will be overall 3 steps then, right? Here I am summarizing the reaction. It is not like a general class. It is not like a normal or regular class. This is summary session only. Yes. So H2O attacks on this carbocation, and later we will be getting OH group on that side. So there is also no stereochemical relationship between the H and OH arrangement. It could be above or below because there is a carbocation intermediate. Okay, H2O can attack from above or below. We don't know. Yes. And that is a product, that is alcohol product. This is one way of adding H2O, HOH addition, and rearrangement is possible due to carbocation formation. Now we have 2 other options also for adding H2O, and in these 2 options there are no rearrangements. One is hydroboration reaction. Okay, one is hydroboration then oxidation. That is another way of H2O addition, and hydroboration occurs in such a way that BH2 unit, this is a bulky group, the bulky BH2 unit goes to less substituted or less hindered carbon. It is steric driven addition mainly. So BH3 will look on the alkene, and it will see which carbon is less sterically hindered. Here 2 hydrogens only, here 1 R and 1 H. So this is more hindered carbon, this is less hindered carbon. So the bulky BH2 adds on this carbon, H goes to this carbon. This is a syn addition. This is a simultaneous addition of H and BH2. Simultaneous addition. Therefore it is a syn addition. On which side H is present, the same side BH2 will be present. There is a stereochemical relationship between H and BH2 groups. This happens in single step. Okay, so this is called hydroboration, and it can go further also. 2 more hydrogens are there, so it can go all the way till trialkyl borane, which you know. You can see the detailed mechanism in your class notes. Here I am listing the major events only. So this happens first. And now oxidation occurs if we provide the sufficient reagents. Oxidation reagent, you know, H2O2 along with OH minus medium. And on this is called oxidation. This was called hydroboration. Hydroboration gave us such a compound, or its more substituted variant called trialkyl borane. And on oxidation, just BH2 is replaced with OH. That is a summary of this reaction. BH2 is replaced with OH. That is called oxidation reaction. And very interestingly, on which side BH2 was present, on the same side OH will come. Okay, on which side BH was present, on the same side OH will come. So effectively, therefore, this reaction is a syn addition of H and OH. Okay, we can call this a syn addition of H and OH also, because OH is attached on same side where BH2 was present. So effectively we can say there is a syn addition. Hydroboration oxidation is a syn addition of H2O. H and OH will be on same side, of the alkene at the end of the reaction. And you can see that no carbocation formation is there, therefore no rearrangement. No rearrangement also. No rearrangement also. Due to non-involvement of carbocation. And other important aspect is that if we have an unsymmetrical alkene, then anti-Markovnikov alcohol will be the major product, right? Because BH2 is coming on the less hindered carbon and there itself OH comes later. Therefore, it looks like an anti-Markovnikov addition of H2O. So, this is therefore called anti-Markovnikov alcohol. Gives anti-Markovnikov alcohol. So, these are the interesting features of hydroboration oxidation reactions. Compared to the previous one, there was rearrangements possible. There is a Markovnikov alcohol formation also because of carbocations, and exactly contrasting is this one. There is no rearrangement at all and there is anti-Markovnikov alcohol formation also. This is just exactly opposite to the first one. And the first reaction was called acid catalyzed hydration. And this reaction is called hydroboration oxidation. That is second way of adding H2O. Now we have one more way of adding H2O, that is oxymercuration demercuration. Let's see that also. Oxymercuration demercuration. Oxymercuration demercuration, the reagent is HgOAc twice and mercury ion adds first. Mercury ion adds first. You can see that this is Hg2 plus. I am summarizing the reaction and these are OAc minuses, acetate, and Hg2 plus attaches on the alkene and gives a cyclic mercurinium intermediate, like we saw halonium intermediate. Hg2 plus adds to give us a cyclic mercurinium intermediate. Cyclic mercurinium intermediate. No carbocation. Therefore, no rearrangement also. Here also no rearrangement because there is no explicit formation of carbocation. So, in this addition of H2O, no rearrangements occur. And then immediately, you know, this we are doing in H2O solvent. If we are doing it in H2O solvent, then this happens. H2O attacks like you saw in the bromohydrin reaction formation. Similarly, H2O acts on this carbon because if the ring has to open, let's assume this way, if the ring opens, then there is more positive charge present on this carbon only because here the positive is more stabilized due to inductive effect of R group. So, H2O, when H2O looks at this intermediate, it sees a more amount of positive charge on this carbon, therefore it is attracted to this carbon and that way the ring opens. And we get RCHOH here, CHG plus over there, Hg2 plus now becomes Hg plus. Okay, and this is now an anti-product. OH and Hg plus will be on opposite side. Cyclic intermediate was there. Therefore, H2O should come from below side only if mercurinium is above. Therefore, it looks like Hg is above ultimately and OH is below. Okay, that is anti-product only, like in the case of cyclic bromonium opening. Okay, it is looking similar to bromonium reaction. And this happens and now we have to remove mercury. So, this we are calling oxymercuration. Till this we are calling the reaction oxymercuration. We have added mercury, we have added oxygen also, that is oxymercuration reaction. This happens sequentially. Next is demercuration. We have to remove our mercury. Demercuration reagent is sodium borohydride. Mechanism is not understood properly. There is no stereochemical importance also in this reaction because ultimately Hg plus, you know, NaBH4 gives H minus and this H minus replaces Hg plus. is H minus replaces Hg plus, and ultimately we don't know on which side the hydrogen is present. It could be above or below. The mechanism is not clearly understood. Therefore, it is easy for us. No such questions can be asked related to mechanism, related to the stereochemical outcome of this reaction, because last step is not clear for anybody. So, we can draw a product like this. Demercuration happened, we can say. There was a demercuration. And demercuration gives us alcohol product. That's it. This is an alcohol. And two important aspects were this: there is no rearrangement in this course of reaction. Not rearranged it is if H is there, OH is here. And it is Markovnikov alcohol also, because cyclic mercurinium H2 attacked on this carbon only. Therefore, OH will every time comes on this carbon, and ultimately on demercuration H will come on this carbon. So this is effectively a Markovnikov addition of H2, or effectively it gives a Markovnikov alcohol without any rearrangement. Without any rearrangement. And here was one variant called alkoxymercuration if we are doing this reaction in alcohol solvent. If the reaction is done alcohol in alcohol solvent, then instead of H2O, it is alcohol molecule, which is also a nucleophile, attacking on the mercurinium intermediate, and we get OR in place of OH. That is only difference. OR in place of OH, like this, HOR, CHH, Hg plus. This is also anti-product, but doesn't matter. This is also anti-product, but the next step is not understood. Therefore, ultimately we are getting some mixed products. We don't know what is happening. So, if we are doing sodium borohydride, that is demercuration, then we can get a compound like this. H hydrogen and OR, right? This is now an ether. And this was called alkoxymercuration, demercuration. Okay, so like we called this two steps oxymercuration, similar way this whole conversion is called alkoxymercuration. We are adding mercury and alkoxy group, right? Alkoxy, mercuration of alkene, then demercuration. Ultimately gives ether product, previously alcohol product. Okay, these are the important aspects related to mechanism of the said reactions. Once again, if you go back to the summary chart, rearrangements is possible. In this case, because in this case there is a first a carbocation intermediate formation due to addition of H plus, and later rearrangement is possible. In this case also, because there is also a similar occurrence at the first step. H plus adds on the alkene, giving carbocation. Explicitly carbocations are formed, and in no other reaction, 1, 2, 3, 4, 5, 6, 7. In these 7 other reactions, totally we have 9. Out of that 7 reactions, no rearrangements. Okay, no explicit carbocation formation. Hope these basics are clear to you. Now we have alkynes reactions also, 2 reactions only mainly. Let's quickly summarize alkynes addition reactions also. Addition reactions of alkynes. Here we have only 2 options, only 2 to remember: addition of HX and addition of H2O. addition of HX gives geminal dihalide. Previously we have prepared vicinal dihalide by X2 addition in CCl4 or CHCl3 solvent. Here we are getting geminal dihalide, and addition of H2O gives aldehyde or ketone. So two new compounds are produced, right? Aldehydes or ketones. So these addition reactions are producing such characteristic compounds. Previously we saw different products only, right? And let's quickly summarize the mechanism of these two reactions also. Let's take an alkyne, R, C triple bond, CH, an alkyne, and try to add HX. Similar way which we saw in the case of alkene, it is a positive part of the adding molecule which adds first on the alkyne also, because alkynes are also more electron rich due to loosely bound pi electrons. And we get RC double bond CH, and H plus of HX goes to this carbon, producing a carbocation like this. This is a vinylic carbocation intermediate. Vinylic carbocation intermediate. No rearrangement. This is not rearranging. Normal carbocations may rearrange. Here no rearrangement. And this reaction produces the more stable vinylic carbocation. Only there is a possibility of vinylic carbocation either on this carbon or on that carbon, right? If H plus goes to this carbon, vinylic cation on this carbon only. If H plus adds on this carbon, we get vinylic carbocation on this carbon. Okay. Out of these two options, anyway one vinylic carbocation has to form. Out of the two vinylic carbocation, this is the more stable vinylic carbocation due to the inductive effect plus I effect of the alkyl group. So that will be forming mainly in the reaction mixture. And it is therefore on this carbon the X minus adds in the later stage. Right? First H plus added, now X minus adds. We get RC double bond CH, H and X on these carbons. No stereochemical relationships as such. Okay. So this is a vinylic halide now. Vinylic halide now. X is attached on the double bonded carbon. Vinylic halide we say. And the reaction will continue to occur. It can add one more HX because it has one more pi bond, right? So next HX addition occurs. HX addition again occurs sequentially. H plus from next HX comes and it adds on this pi bond. And there is also two possibilities. Either H plus can go on this carbon creating positive on that, or H plus can go to that carbon creating positive on this carbon. The second one is favorable way because of the plus R effect of halogen. Okay, the next H plus adds to the previous carbon itself. Okay, wherever the first H plus was added on the same carbon, the second H plus also adds, because then we get a more stable carbocation. This is more stable due to the plus R stabilization of the carbocation. Okay, plus R effect of the halogen atom, and this forms. And now this is not rearranging. Okay, no rearrangement. This carbocation is stabilized, therefore no rearrangement. And in second it happens, X minus attacks on the same carbon wherever positive is present, and we get a product like this, and clearly it is a geminal dihalide. So alkyne HX addition gives us a geminal dihalide, which is a characteristic of mechanism. Okay, positive charge forms on the carbon where X is attached due to its greater stability. Therefore second X also comes to this same carbon, resulting in a geminal dihalide. So there is a 4 minimum steps, right? First step, second, third and fourth. H plus X minus, H plus X minus. Sequentially things occur. And this is the final outcome, geminal dihalide. Okay. So since alkynes had 2 pi bonds, it could add 2 HX molecules. Now let's see addition of H2O. Addition of H2O, the reagent is addition of H2O, the reagent is mercuric sulfate, dilute H2SO4 and then heating, generally 333 Kelvin. This is the reagent. So first thing that happens is H plus addition only. We are not looking into detailed mechanism here. We are summarizing the important events of the mechanism. On mixing alkynes with mercuric sulfate containing H plus, first thing happens is addition of positive part, which is H plus. RC double bond CH. H plus comes on that carbon, creating the more stable vinylic carbocation again. Vinylic carbocation, more stable one will be forming. And more stable vinylic carbocation forms later on this. Next, who is there? H2O solvent is there, right? Reagent is HgSO4, dilute H2SO4. Dilute H2SO4 means solvent is water and it is present in plenty. Right. So in this medium, the nucleophile, the powerful nucleophile is H2O solvent only. SO4 2 minus is not a good nucleophile. Hg2 plus is not a nucleophile at all. And then H plus is the other component present in the medium, that is also not a nucleophile. So after the first addition of H plus, then only H2O can attack on the carbocation. So H2O attacks on carbocation, on the more stable vinylic carbocation, and gives us a compound like this, RCOH double bond CH2. This is now an enol. This is an enol or vinyl alcohol. You know that enol is not very stable. It quickly undergoes isomerization or tautomerism, the so-called keto enol tautomerism, to form the more stable carbonyl compound, right? RC double bond O, CH3 is formed. This is a ketone and this is aldehyde if R is H, meaning if we start from acetylene, then we can get an aldehyde. Otherwise, it is like a ketone because there is a Markovnikov addition of H2O happened, right? H plus on the terminal and OH is on the middle carbon. This is like a Markovnikov addition according to mechanism. And so generally we are getting ketone in this reaction, and if R is H, then there is no option but to give aldehyde. Okay, that will be acetaldehyde then. It is for this reason that only one H2O can add on alkynes, not two H2O cannot be added on alkynes, because on first addition of H2O we get an enol which directly tautomerizes, which isomerizes to a stable product ketone. Okay, normally we can neglect the reverse also because enol form will be present in less than 5% only, although it is an equilibrium mixture. And in greater than 95% will be keto form only. So we neglect the reverse reaction. We can write using a single headed arrow, single direction arrow mark also. Okay, no mistakes if we use this arrow mark, but practically we will not be having any of this. We will be having solely that particular structure in the final mixture. Okay, so this is the hydration of alkynes. Hydration of alkynes. Only one H2O we could add, but HX we could add 2, right? HX we could add 2, H2O we could add only one H2O. Yes. So that way we looked into the 11 different reactions, right? So far we have discussed about 11 reactions, all falling in the category of addition reactions and very important reactions, very frequently asked also. Now let's see. I have compiled here some 17 or 18 questions from the past 11 years, which is kind of exclusively from this section, okay, which is not mixed with other sections in general. Okay, we cannot have such questions. Such questions are very difficult in our JEE exams. Questions are generally mixed type, and if there is an addition reaction, the next step there will be some elimination, some other reaction also clubbed along with the same question. Okay, but I could find this much questions which covered only one aspect, only one sort of reaction. Yes, let's see them one by one. So these are problems related to addition reactions of alkynes and alkenes, which we have discussed so far. Okay, the first question is given. Okay, this compound is there. Bromine 1 equivalent is applied. Bromine 1 equivalent is applied in methanol solvent. Here you can see that there is an alkyne, there is an alkene present. There is an alkene present here. Alkene, and there is a ring also. We know that bromine simply does not add to the ring unless the ring is highly activated. This is not highly activated ring because we have one acyl group here which is in resonance also, not highly activating, and this is deactivating also. So bromine just does not directly add to the ring like they have shown in this option or that option. So that simply does not occur in this case. We need to apply some aluminum chloride or such catalyst also if this product has to occur. Here that does not occur. Okay. Yes. Now the other compatible substrate is alkene present over here. Okay. This alkene bromine interacts. We know the sequence of interactions. Let me redraw the structure once again. I am simplifying this like OAC and CO. Okay. You know that if bromine molecule is given, Br plus is the first species that attacks on the alkene, giving rise to cyclic bromonium intermediate. Remember the mechanism, C double bond O and Br plus forms like this, cyclic bromonium intermediate forms. Now you can see that our solvent is methanol, not CCl4, not H2O. This is an alcohol which is also nucleophilic, right? Therefore, what happens is that in the next step, methanol itself attacks with its nucleophilic power either on this carbon or on that carbon. That we have to decide. Okay, where methanol will attack. For that, we need to apply our logics, which I have mentioned previously. You just try to open the ring like this. This is one way of opening the ring, or this is another way of opening the ring. Right. Compare the two structures. If we open ring like this, we can get a positive on that carbon. If we open the ring like this, we can get a positive on this carbon. Whichever is more stable carbocation, that will happen, right? Whichever is more stable carbocation, that will happen. You can see that this is very less stable. This is very less stable carbocation because it is adjacent to a strong electron withdrawing group. So this is the more stable carbocation. This is the more stable carbocation. So this is selected, right? So the compound will have a more character of this will have a greater character of this carbocation, very less character of that carbocation. Therefore, methanol is mainly going to attack on that carbon only, because their positive is more stabilized. Thus, methanol decides to attack on that carbon and the ring opens like this. Okay, ring opens like this and we get OAC, C double bond O, Br and OMe there. OMe there. Let me redraw it. Okay, on this carbon OMe, there bromine. Right, that is a final product. So we just applied whichever mechanism we have learned. There is a first formation of cyclic bromonium, Then wherever positive is more stabilized, there the nucleophile will attack. If it was H2O, H2 attacks there. If it is methanol, methanol attacks there. If it is ethanol, ethanol attacks there. So similar thing happens every time. Now let's identify this product from options. This is option 2. You can see bromine on this and OMe on that carbon. No other changes occurred. So that is our final answer. So this is halogen addition in alcohol solvent. And clearly it is a halo ether. Halogen addition in alcohol solvent gives halo ether. Okay, now let's see the next question. Which one of the following alkenes when treated with HCl yields majorly an anti-Markovnikov product? Okay. So these are alkenes. Alkenes treated with HCl. Alkenes treated with HCl. Here, let me redraw it if it is not clear. I think there is some clarity issues. CH double bond CH. This is the first alkene. And secondly, they have given Cl, CH double bond CH2. And third, OCH3, CH double bond CH2. And finally, NH2, CH double bond CH2. These are the different alkenes given to us, and they are trying to add HCl on it. If you are trying to add HCl, first H plus from HCl adds, we know, on alkenes. And if first H plus from HCl adds on alkene, you can see that in this case, in the first case, either H plus can go to that or this. Wherever we get more stable carbocation, accordingly addition happens, right? And if H plus comes here, a primary cation will form. If H plus goes there, a secondary cation will form. But the problem is that this is a very strong minus I, very strong electron withdrawing group, very strong electron withdrawing group. So if there is a strong electron withdrawing group present on this carbon, adjacent carbocation will be highly destabilized. Therefore, that will not form. So hydrogen plus is added on this carbon, creating a positive on there. Therefore, first we will be getting mainly such an intermediate where H plus is on this, creating a positive on terminal. Then Cl minus adds on this carbon. So we just applied the logics of carbocation stability here. CF3, CH2, CH2, Cl here. This is now an anti-Mark addition product because Cl minus goes to less substituted carbon, H plus on the more substituted carbon. Okay, this is anti-Mark product. Now let's see the other options also. If you are adding HCl on this, H plus from HCl adds, in this case on this carbon only H plus goes, because if positive is created on this center, chlorine has plus R effect which stabilizes its octet. Okay, if the carbocation is formed on that carbon, then there is no direct stabilization of carbon, the carbocation. If carbocation is present on this carbon, then it can directly stabilize it by plus R effect. Therefore, on this carbon only C plus forms, Cl, CH plus CH2 H over this carbon. Okay, so this is the more stable one due to the plus R effect of the Cl group. Next, Cl minus can attack on this carbon, giving rise to a compound like this, CHCl, CH3. So that is a major product, that is now a Markovnikov product because Cl is on more substituted carbon. Now, next H plus again adds to terminal carbon because if positive is present on this carbon, it can get the plus R stabilization of OCH3 group, right? Therefore, positive is present on the adjacent carbon of the electron donating group. Okay, here we will be calling these groups electron donating groups. This is also electron donating group, and all of them have plus R effect, which highly stabilizes the adjacent carbocation. And Cl minus later adds on this carbon, creating OCH3, CHCl, CH3 as the product, again Markovnikov product. Okay, so this was simply based on carbocation stability. NH2 CH plus CH2 hydrogen adds to this carbon, and positive on adjacent carbon of amine group stabilizes it by plus R effect. The good thing about this stabilization is that by this donation everybody's octet will be complete. Otherwise, if this donation is not there, this cationic carbon will have a sextet of electron only. There is only 6 valence electrons, so it is very electron deficient then. But now it is balanced. The octet is complete for everybody due to resonance. Therefore, this is highly favored in this way only. But in the first case, the only minus I effect was present for this group, CF3 group. Therefore, positive will stay as much as distant as possible from this group to have a better stability, right? In the last case, Cl minus adds to this carbon, and we get NH2, CH, Cl, CH3 as the product. This is also Markovnikov product. Yes. So we saw electron withdrawing group and in electron donating groups in every other cases. This is the next question. Major product of the following reaction is CH3. Let me redraw the question once again. CH3 is acetylene. This is propyne. CH3C triple bond CH. Then first they are adding DCl, one equivalent, and then adding Di. Okay, what happens? So this is alkynes and alkyne HX addition. We know first H plus adds, then Cl minus. First H plus adds, then I minus. Similarly, DCl also adds to this alkyne. Okay, let's see. First D plus from DCl adds, and we get vinylic carbocation on the middle carbon. That is a more stable one. Then D goes to that carbon. More stable vinylic carbocation forms, and then immediately Cl minus adds on that vinylic carbocation, giving us a vinylic halide product. Cl double bond CDH, vinylic halide product. So only one equivalent of DCl we are providing. Next we are providing Di. On giving Di, again the same thing happens. D plus from Di adds, giving rise to the more stable vinylic carbocation, which is on alpha carbon of the haloalkene. CH3 CCl plus comes here, and CDH, the second D also goes to that carbon only, creating a more stable positive charge. This is more stable due to the plus R stabilization of chlorine group. And now I minus attacks. I minus attacks on this carbon, CH3, CCl, I, and CDDH. That is a final product. Now this is a geminal dihalide. We know alkynes on adding HX will produce, on adding 2 molecules of HX, produce geminal dihalides, and HX could be HCl, HBr or HI, and you know on using D version of HX, the mechanism does not vary because isotopes are similar in chemical properties, just that rate will be little different, but overall reaction pathway will not be different even if you use isotope labeled compounds. Yes, so analogous product will be obtained, and the product is CH3, CiCl, CHD2, right? CH3, CiCl, CHD2 is the product. Option 4 is the correct choice. Next question, the major product of the following addition reaction is, we are given with propene, chlorine H2O is the reagent. Chlorine HCl, they can also write HOCl, both are equivalent. Let's see what is happening in this reaction. CH double bond CH2, we are adding chlorine water on propene. Then what happens initially, Cl plus from Cl2 adds on the alkene, giving rise to cyclic halonium intermediate. Okay, CH2 Cl plus forms like this. Cyclic halonium intermediate is formed, which is highly stabilized due to complete octet of all atoms involved. Okay, now next thing that happens is, since we are using H2O solvent, it is nucleophilic. Okay, if we are using CCl4, then Cl minus goes here, we get a vicinal dihalide. But if we are using H2O, H2O attacks mainly on the cyclic halonium intermediate, giving rise to CH3, CH, OH group on this side, CH2, Cl on that carbon. Okay, such a compound is produced, and you know that H2O or alcohol attacks on this carbon only, not on that carbon, because here positive charge is more stabilized. If you open the chloronium ring, you will find that on this carbon only positive is more stabilized. Therefore, we can say that in this compound there is a more fraction of positive charge present on this carbon than on that carbon. Therefore, H2O attacks on this carbon, opens the ring this way. Yes. So, this type of a halohydrin is produced. You know, halogen in water will give us halohydrin. This is a chlorohydrin, and this is a Markovnikov addition. We can call this a Markovnikov addition of HOCl. Okay, remember everything. This is a Markovnikov addition of HOCl, and the product will be option 2, CH3, CHOH, CH2, Cl. Okay, next question is the increasing order of boiling points of the major products. You can see that questions they are asking in different ways. This is not directly a product prediction type question. You can see that they are mixing with some physical properties also, boiling point comparison. Okay, anyway, let's try to do it. Identify, first of all, we need to identify A, B, C, their correct structure, then compare their boiling point, right? Okay, let's see. We can easily find that all are addition reactions of alkenes, and first reaction is HBr in presence of a peroxide. Then therefore, what happens initially is that Br dot adds, right? Br dot, it is producing, this combination is producing bromine free radical, and bromine free radical attacks on the alkene. Okay, either bromine free radical can go on the terminal carbon, or bromine dot can go on the middle carbon. Wherever it goes, we have to get the more stable free radical intermediate. Okay, with that sense, with the we have to get a more stable intermediate. Therefore, we should be adding bromine dot, or we can say that bromine dot adds to the terminal carbon only, because then free radical is produced at the middle carbon. Right. So here we will be getting a compound like this. This is the intermediate, more stable secondary free radical, and later H is added. H from a second HBr adds on that, giving rise to such a compound, H here, Br there. Okay, so that is the mechanism of the first conversion. So we actually got N-bromobutane, right? Normal bromobutane we got. This was but1-ene. Yes. So but1-ene gave us compound like this. Now HBr addition on another alkene, which is 2-methylpropene. 2-methylpropene HBr addition, simply if we do, first H plus from HBr attacks, H plus from HBr attacks to give us a more stable carbocation, which is a tertiary here, right? First we will get a carbocation on this carbon, H plus goes to that carbon, and this will not undergo any rearrangement. This is the most stable intermediate here, and now Br minus adds in the next step, and we get a compound like this, which is a tertiary butyl bromide, right? So compound B is tertiary butyl bromide. Now, third case, we are taking butadiene HBr addition, simply HBr addition, therefore H plus adds first. H plus goes on this or that carbon, both are equivalent, therefore no problem. Add it somewhere, we get a positive charge, a secondary carbocation, which cannot rearrange now because if we add a hydrogen, if we shift a hydrogen from here to there, we will be getting a secondary carbocation only, same carbocation only, secondary butyl carbocation only we will be getting. So here no options for rearrangement. This is the most stable intermediate for this reaction. Therefore we can proceed to the last step. We can add Br minus on this carbon, we will be getting Br and H here, right. So that is the third compound, the product, that is 2-bromo-butane. So all are bromobutanes, all have same molecular masses. Now we have to look at the branching only. This is the least branched compound, therefore boiling point will be highest for A. Boiling point will be highest for A, and there is only one option in which boiling point of A is highest. So this is the correct answer, and we can see that B is highly branched, heavily branched compound. It is tertiary butyl bromide, so it has the lowest boiling point. As the surface area of molecule decreases, boiling point keep on decreasing. So 3 is the correct answer. Now next one, the major product of the following reaction is, we are given with an alkyne. We are doing hydration. The reagent, let me rewrite it. We have a ring, a nitro group, then C triple bond C, then another ring, a noemi group, and the reagent is the usual hydration reagent, Hg2 plus H plus in H2O. Okay. So in presence of Hg2 plus, H plus adds on alkyne first. Okay. First H plus adds on alkyne in presence of Hg2 plus. Then we can get two different, since this is an unsymmetrical alkyne, we can get two different carbocation. Right. So in this carbocation, either we can keep H on this carbon, then positive on this, or H, if we keep on this carbon, positive will be present on that. And you can see that here is a strong electron withdrawing group and there is a strong electron donating group present on either side. Therefore, a positive charge adjacent to electron with donating group will be more stable, and our carbocation on this carbon will be highly less stable due to minus R effect of this group. So positive charge will be coming on this carbon where it is more stabilized, and H will be going to this carbon. So using logics of carbocation, we will identify the more stable carbocation like this. H plus goes there, positive comes on this carbon. You can easily see that this OCH3 serves to stabilize this carbocation by plus R effect. Okay. So plus R stabilized carbocation is obtained. Now H2O adds, H2O adds on this carbon. We get NO2, C double bond C, and an OH, then a ring OCH3. This is an enol. This is an enol which quickly tautomerizes to more stable keto form. NO2, CH2 C double bond O ring OCH3. Okay, this is the correct final product. We can add only one H2O, although there are two pi bonds, because first addition of H2O gives us an enol, which itself tautomerizes to more stable product, a stable product. Yes, so let's identify the option. This compound is option 3. Okay, ketone close to OCH3 containing ring, anisole ring. Okay. So you can see that every time we are using mechanism, the simple mechanistic aspects to predict every products. Yes, so let's continue. This is the next one. What is the major product of following reaction? Okay, we are given with an alkene. Let me redraw it. CH3, 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 then CH double bond, CH2. This is treated with HI. This is treated with HI. You can see that this is addition reaction of alkene, and first H plus from HI adds, because this is alkene, this is electron rich, and it leads to the more stable carbocation intermediate. Positive on this carbon will be formed CH plus, then CH2 there H plus. Right, more stable carbocation forms, and you can see there is a possibility of rearrangement as well. So thus that happens, it gives rise, the rearrangement leads to a tertiary carbocation like this, CH3, CH3, CH, there one CH3 and one more CH3. Right, that is a most stable intermediate for this reaction. This was a secondary, that is now a tertiary carbocation. This cannot rearrange further. Now our I minus will come. I minus adds to the carbocation. We get iodine on tertiary carbon. So that is a tertiary iodoalkane now. That is the final product. So let's identify this product. Option 3 it is. Okay, so we must know that first H plus adds according to the reality, according to the mechanism, and if H plus adds, then a secondary cation forms, which is a more stable one. Okay, either a primary or secondary will form first, and then quickly it rearranges also, because there is a possibility of tertiary formation also. That happens, and since there is a carbocation involvement, we know that in HX addition reactions of alkenes, not in alkynes, in alkenes there is a possibility of rearrangement, and it is an example for such rearrangement containing reaction. Yes, so that happened. I minus attacked in the last stage. We got option 3. This is the next question. We are given with an alkene and HBr CCl4 is given. CCl4, you can see that this is a solvent. This will not interfere directly in the reaction. This is just a solvent. This is non-reactive, non-nucleophilic solvent. So don't look at that solvent. Only focus on the reacting part, that is HBr. Okay, let's do the reaction. Alkene is given. HBr is applied. We know alkene it is, electron rich it is. Therefore, it interacts with positive part of the HBr, and it first forms a carbocation intermediate. Okay, a carbocation intermediate, whichever is more stable, that forms first. This is the first formed carbocation. A primary possibility was there, a secondary possibility is there. Secondary is formed first. And you can see that it can rearrange to a tertiary carbocation by a methyl shift. So methyl shift occurs next, and methyl group goes there, positive reaches here. Such a structure is obtained. And now this is a tertiary carbocation. This cannot be stabilized further. This is the most stable intermediate. So now we can proceed to the last step of the reaction, which is Br minus attack. So Br minus goes to this carbon. we get a tertiary bromo compound, right? So this compound is option 4. Okay, so we know that H plus adds first, it forms carbocation explicitly. So carbocations, all information, all knowledge we can apply here. Carbocation show rearrangement, so we did rearrangement. We identified the most stable carbocation intermediate possible in this reaction settings, and then we are proceeding to the next step, bromide attack. Next question is this one. An alkene is given again. So you can see that alkenes are mainly asked in exams. Very rarely you will find alkynes reactions in question papers. These are all previous questions from last 11 years. These are not the only questions in which addition reactions, these reactions are present. These reactions are present in other questions also, just that in other questions there will be other reactions also present along with this. These are purely, mostly purely addition reactions only. But here you can see an exception. This is, first step is an addition reaction, then we are doing a nucleophilic substitution also. Okay. Anyway, let's do the first step. They are applying HBr plus a peroxide here. HBr plus a peroxide is taken. HBr plus peroxide, you know, it gives us bromine free radical, and bromine free radical interacts with this alkene first. We have to write the more stable alkyl free radical intermediate. So more stable alkyl free radical intermediate will be here, and therefore Br goes to there. If Br attaches middle, then primary alkyl free radical will form, that is less stable. If Br attach on terminal carbon, then secondary alkyl free radical will form. This is more stable. So this is formed. Okay, no rearrangement. No rearrangement for free radicals. And here, then HBr's, next HBr's, H dot will come, and we get compound like this, and that is the first product. That is the first product. Then they are doing a Schwarz reaction. Okay, they are giving a Schwarz reaction condition. You know, you can give COF2 or Hg2F2 or AgF, several reagents, you know, SbF3. Okay, apply one of those reagent, there occurs an SN2 reaction, and F minus is replaced. Br is replaced with F, and we get such a product at the end. And so this option is for option 4. Here they have, you can see that one bromine was present on the ring. On the ring, haloarenes, it is haloarene is not substituted generally. Haloarenes, C halogen bond is stronger, CX bond, that is not taking part generally in our reactions. Okay, reactions of haloarenes requires very harsh conditions. Okay, so from starting till end, that Br was staying on the ring itself, that is not altered in any way. Given below are two statements. One is labeled assertion and the other is labeled reason. Okay, assertion: treatment of bromine water with propene yields. Bromine water with propene yields. One bromo propan to all. One bromo propan to all. That is assertion. And reason: attack of water on bromonium ion follows Markovnikov rule and result in one bromo propan to all. So this is mechanism based. Major product related question it is. So we should know mechanism, and if we think about the mechanism of bromine addition, first there is a bromonium ion formation, cyclic bromonium intermediate formation. Right. This is the first step that occurs, and then since we are using H2O solvent, H2O attacks on the ring, H2O attacks on the ring on the middle carbon, only more substituted carbon, then we get this product. Yes, that is correct. This product only we will be getting. This is a Markovnikov addition of HOBr therefore, and they have mentioned all the details of mechanism. Attack of water, yes, attack of water on bromonium ion follows Markovnikov rule, that is correct. H2O OH goes to more substituted carbon and results in 1-bromopropanol. That is true. Br plus on less substituted and OH minus or H2O on the more substituted carbon. That is true entirely. So both A and R are true, and R is explanation of A. Therefore option 3 will be our answer. So you can see that to deal with such questions, we need to have an idea of mechanism also. So this is understanding based question. Yes, that happens now. Now the next question is, amongst the following the major product of the given chemical reaction is. Okay, an alkene is given, and bromine is added in methanol medium, Okay, so first bromine plus adds, right? We know halogen alkene reactions, every time bromine plus adds on the alkene, creating a cyclic bromonium ion intermediate. Like this. Okay, like this. And now in the later step, since we use methanol, if we use CCl4, then it is Br minus going to attack, and if we use H2O, then is H2O going to attack. And since here it is CH3OH, it is CH3OH that acts as the nucleophile and opens the bromonium ring. Okay, methanol goes to attack on this system either here or there. We have to decide. Okay, we have to decide. For that we can use the logics. Just try to open the ring and see where positive is more stabilized. Open the ring like this, then positive is on this carbon, and if we do the other way, positive on that carbon. Both are secondary carbocations, but you can see that this is an electron donating group, ether group. This has plus R effect, so this stabilizes this cation much. So this is more stable carbocation. This is less stable carbocation. So more stable carbocation is the more formed carbocation, and therefore CH3OH goes to this carbon mainly because there it finds more fraction of positive charge. Okay, so CH3OH attacks on this carbon where positive is more stabilized and opens the ring like this, and we get OCH3 on this carbon and Br on that carbon, right? So that is a final product. So we have applied our mechanism knowledge in this reaction also. Now let's go to the options. Let me redraw it. In the option they are using wedge dash notations. Let's say this is like this, and these are both wedges, and this is wedge and dashed. This is like this. Okay, let's say options are given like that. If that is the case, wedge or dash, that we have to decide. Okay, you know that this is a cyclic bromonium ring opening. So if the bromonium ring was formed on the above side like this, let me apply a wedge on that side. So if bromonium formed like wedged bromonium, then you know that this bromine will be wedged ultimately and methanol will be approaching from below side. Therefore methanol will have a dashed line on it, right? This is one possibility. Or if this bromonium was formed on below side like this. Then methanol attacks from above only, okay, from above only. Then bromine will get a dashed line only, and this side methanol OCH3 group will be getting a wedge line, right? Therefore, we say this is anti-addition. Remember, we have mentioned bromine addition in CCl4, in H2O, in alcohol also. They are anti-additions because of this cyclic halonium intermediate, and the ring is opened, right? Therefore, if bromine is ultimately above, OCH3 must be below only. And we have to identify either this structure or that structure. Both are possible. Okay, one of them. Okay, both are formed in equal amounts. One of them we have to identify from here. And if you see, first option we have such an arrangement: OH3 above, OCH3 above, Br below. Right? In second case, you know, both are dashed, both are wedged. Okay, that does not happen. This is syn addition then. But we know actually it is an anti-addition. This is a syn addition product. This is an anti-addition product, right? And here, you know, OCH3 is on that carbon. That does not happen. That is minor only. Okay, OCH3 mainly comes on this carbon only because there only positive is more stabilized in the bromonium. Yes. So only option 1 will be matching here. So we will pick that option. Okay. If this structure was present in the options, then we will be choosing that also, right? Okay, both are okay. And if it was a multiple correct type question, then you can pick both. If present, we can pick both. And if in this question, if this is a single correct question, if both are present, both will be accepted as right answers. Next question is pH double bond CH2Br with HBr. Okay, this is an alkene. You can see an alkene here and HBr addition. We know alkenes first interacts with H plus and it forms a carbocation either here or there. Whichever is more stable will be formed in greater amounts. You can see that here we have a benzene ring. So this is a benzylic position. Here positive charge will be more and more stabilized. Okay, therefore H plus goes there, positive comes here. And the first step product will be benzylic carbocation like this. Benzylic carbocation very stabilized. Now Br minus comes on that carbon. We get pH, here Br, and previously Br was present there. Okay, this is formed and this product, okay, option 3 will be the correct choice. This is just addition reaction. We need to identify, we just see the functional group present in the compound, that is an alkene. Okay, alkene with HBr, you know the mechanism of addition. H plus adds first, then on more stable carbocation Br minus adds. We get the haloalkene product. Major product of the following reaction is, okay, we can see an alkene here, an alkene there also, we are giving 2 HBr. Yes, so first let's take the left one, the left side alkene. On the left side alkene, first let's say H plus adds, and H plus adds to give more stable carbocation. Therefore, you know H plus goes there, positive here, because this is an electron withdrawing group, right? This has minus I minus R effect only, no plus effects. Therefore, it is destabilizing the carbocation. So, the H plus attached on this side, creating carbocation there, and then Br minus attacks on this carbon. We get bromine here. So H there, Br here. This is like a anti-Markovnikov addition because this was an electron withdrawing group. Now on the next side, if you consider HBr addition, again H plus from next HBr adds, H plus from next HBr adds, so that more stable carbocation is formed, and this time the normal case it is positive is formed in the middle. Okay, positive is formed in the middle, and this is the more stable. This is secondary carbocation more stable than the adjacent, than the terminal primary carbocation. So this is formed, and later Br minus attacks, and we get final product Br, CO, O, Br here. So first HBr like this, second HBr like that. This is a mark. This is anti-mark addition. That is a mark addition. Okay, and that happens. We get this is the correct answer. Next question. Let's see. Major product B of the following reaction is. Here we are taking the first portion only. The second portion is related to ethers reaction. And first portion reaction, let's solve now. CH3, C double bond, CH3, bromine addition, first cyclic bromonium forms. So CH3, C, and there a cyclic structure CH, CH3 is formed, and then you know we are using methanol here. We are using bromine in methanol solvent, so methanol will attack and opens the ring. CH3OH, CH3OH, you know it attacks on this carbon mainly because here positive is more stabilized due to 2 plus side donations. So methanol mainly attacks on this carbon, and you remember methanol or water attacks on more substituted carbon of the cyclic bromonium, cyclic halonium intermediate. Okay, we get CH3, C, CH3, here OCH3, and then CH, there Br, and CH3. This is the first product. This is the first product. You can see that this is a halo ether. This is a halo ether. And now, halo ether, this is A. Okay, you know that to solve this question, we should be having 100% clarity of the first compound. Then only we can go till B. Okay, the question is, what is B? Okay, next reaction is related to ethers, nucleophilic substitution reaction, that we will be dealing in the later section. Okay, for the time being, let's quickly answer this second part. OCH3 will be breaking in this manner. Here I comes, there H goes, so HI is added in this manner, and we get a tertiary alkyl iodide and methanol. Okay, that is the final product. That is the final product. Okay, so the final product will be therefore CH3CI. This is the final product. CH3CH3C, there instead of OCH3 we will get I, and then CHBr CH3. Okay, that is reaction of ether. That is reaction of ether. That is an SN1 reaction of ether. We will see later. Okay. So be clear with the first compound A, that is related to addition reaction of alkenes. Choose the correct option for the following reactions. This is hydroboration oxidation, B2H6 then H2O2OH minus, and that is oxymercuration demercuration reaction. And first hydroboration, you know the first step. There is HBH2 addition, BH2 goes there is less hindrance on that side, H comes on this side. So CH2 single bond CH2 BH2 will be first intermediate. Let's quickly analyze the reaction pathway once again. Okay, on BH3 addition, we get CH3, 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 CH, here H, and CH2, there BH2, right? You know BH2 unit, that is relatively bulky unit, that goes to sterically less hindered side. Yes. Then on oxidation, that is hydroboration, then on oxidation, H2O2 bar OH minus, BH2 is just replaced with OH, CH3, CCH3, CH3, CH2, CH2, OH. Okay, this is formed. That is called B here. Okay, B is the anti-Markovnikov alcohol. We know, even if we don't know the final answer, we know the correct option here is yes, B is anti-Markovnikov product, that we know, because this is hydroboration oxidation of unsymmetrical alkene. Now let's look at the right side, that is oxymercuration, demercuration. First they are applying mercuric acetate, then we know CH3, 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 CH, CH2, Hg plus ring happens. That is cyclic mercurinium ion intermediate. And on the cyclic mercurinium ion intermediate, since we use H2O, they have mentioned H2O. Therefore, we will take H2O to open the ring. If they had used alcohol, then it is alcohol which attacks on this carbon. H2O attacks on this carbon where positive is more stabilized, like you open cyclic bromonium intermediate. Both are analogous. Okay, H2O attacks the ring this side. Ring is opened like this. We get CH3. Everybody stays at their own location. No rearrangement in these two reactions. OH, then CH2, Hg plus. Now we perform demercuration. Reagent is given on the arrow mark. NaBH4 is added. NaBH4 added, then we get CH3C, CH3, the tertiary butyl group is unaffected. CH, OH here, CH3 is obtained. Okay, mercury is removed, demercuration. That is the so-called product A. Product A is Markovnikov alcohol, therefore, and product B is anti-Markovnikov alcohol. And in both these reactions, there is no involvement of carbocation intermediate, therefore no rearrangements also. Okay, so be clear with every aspect of these two reactions. So you can choose as option 2. Next question, the major product of this reaction is okay, we have two alkene units, one there and here, and 2 HBr we are adding. Okay, let's do it sequentially. This is the alkene given to us, CH3, NO2, and let's first add on this alkene that is electron richer because of CH3 group. And first H plus adds, apply the same mechanism every time. First H plus adds, we get a carbocation. More stable carbocation will form in greater amount. And there Br minus attacks secondly, and we get CH3, Br like this, and NO2 alkene. Next thing that happens is second HBr addition. So second H plus from second HBr comes and adds to this alkene, and on this alkene you know that on this alkene H plus goes to this carbon and positive is created here because NO2 is a strong electron withdrawing group. Okay, if H plus goes here, positive is on this carbon, that will be highly destabilized. Therefore, this is happening In the second case, okay, H plus adds to the carbon where NO2 is attached. The real mechanism is different. Okay, even in case of carbonyl group and nitro group, the real mechanism is little different, but this is the ultimate result. I am summarizing the reaction here. Therefore, you do like this, H plus you add on this carbon so that a more stable, better carbocation is formed, and later Br minus adds on this carbon, we get Br there and NO2, here CH3, and on CH3 attached carbon we have another Br. Okay, that is the final structure. And this is compound 3. So that way HBr additions we can do looking at the stability of carbocation intermediate. So that is the next question. A conjugate diene is given. Conjugate diene is given. And we are adding HBr onto it. Again the same thing happens initially. H plus adds first. H plus has a lot of options here. H plus can either go to the terminal carbon creating a positive one here, or it can attach on this carbon creating a positive on this side, or other option is leaving this alkene as such, H plus can go on this carbon creating a positive on that carbon, or one last option is positive on this carbon and H on that carbon. Okay, like this there are, since there are two pi bonds, there are 4 possibilities of carbocations, and out of which whichever is the more stable one, that will form. Okay, that will form. So you can easily see that this is an allylic carbocation, this is not allylic, very less stable, this is not allylic, very less stable, this is also allylic carbocation. Okay, out of these 1 and 4 allylic carbocation, this is the most stable one because this is a tertiary also, tertiary allylic carbocation, that is a secondary allylic carbocation only. So that is also not formed in greater amounts, this is formed in major amounts. Okay, this is the most stable carbocation. So this is the first carbocation that is forming in the reaction mixture. Now there is a problem. You can see that this carbocation has 2 resonance structures. Being an allylic carbocation, this has 2 resonance structures like this, either this or like that. Okay. So the actual intermediate is a resonance hybrid of both. Actual intermediate, actually we have only one intermediate, but for that intermediate 2 hypothetical structures are possible. So the real intermediate is like resonance hybrid of both. Therefore a positive is delocalized like this. Okay, that happens, and the positives are on this carbon and that carbon. So it happens that in next step, when Br minus approaches this intermediate, Br minus can either go to this carbon or Br minus can go to that carbon. One of this happens, or both of this happens, whichever is happening in greater amounts, that is a question, but it's a major product, that is a question. Okay. So know that before going to the next step, know that there is only one intermediate here. Okay. This structure has, and this is just a hypothetical resonance structure, this structure is this, and this has another resonance structure also, and the actual intermediate is therefore like this, which is a hybrid of these 2 structures. This is hypothetical, this is hypothetical. Okay, this is the actual structure. In the actual structure, Br minus has 2 options, either here or there. Okay, whichever is happening in greater amount, that we need to see. Okay, let's see. For that, let's take help from these 2 hypothetical structures. Okay, know that these are not different, these are single only, but there will be difference in the product, right? Yes. If this attack occurs on that, this is the final product, and if attack, let's say this is 1 and that is 2, yes. If attack 1 happens, this is the final product. If attack 2 happens, this is the final product, right? Now decide. Both can happen. Whichever happens in greater amounts is based on stability of the final product. Okay, look at the 2 final products. Which is more stable? This is more stable product because this alkene is more substituted alkene, right? This is more stable alkene. This is less stable alkene. This is a terminal alkene. The hyperconjugation structures are very low. Here they have a lot of hyperconjugation structures, and this is more stable alkene, therefore this is less stable alkene. So here the more stable alkene product forms in greater amounts, right? The more stable product is this one. So this is the major product of the reaction. More stable product. Since here we don't have two intermediates, from single intermediate two products are possible. In such cases, what we will look into is, we will look into the stability of both the products obtained from the same intermediate. Then decide whichever is major. This is more stable product. Therefore, this is the major product. This is the minor product of this reaction. This is a minor product of this reaction. Okay. So let's see. The option 3 is the answer. This is the this compound. Okay, you can see this is the minor product. That is the minor product. Yes. And now one more difference is that you can see that this is the major contributing structure, and this is easy to form because positive charge is mainly located on this carbon, being a tertiary carbon, right? Positive charge is less present in less amount only on this carbon, right? Therefore, it is easy for bromide to attack on this carbon because of greater fraction of positive charge, and relatively difficult to attack on that carbon. And easy means lower is the activation energy barrier, difficult means higher is the activation energy barrier. So it happens that under normal temperature conditions, whichever leads to major product, whichever leads to the more substituted product, that will happen irrespective of the activation energy barrier. But if you are using a low temperature condition like minus 50 degrees Celsius, let's say, such low temperature conditions at negative degree Celsius temperature, let's say, then you know that activation energy barrier cannot be crossed by the reactants. Therefore, in that case, at low temperature conditions, whichever is easy to form, that will form in greater amounts. That is this product. Right. Therefore, you remember this is called kinetic product, that is called thermodynamic product. More stable product is thermodynamic product of a reaction, and easy to form product is kinetic product of the reaction. Kinetic product, if it is less stable, kinetic product becomes the major product if temperature is very low for the reaction. Okay, if the reaction temperature is low, then it cannot cross that higher activation energy barrier. Therefore, mainly the reaction proceeds through the lower activation energy pathway and giving rise to this product, which is less stable actually. At normal temperature condition, any barriers can be crossed by reactants. Therefore, it looks into the final stability of the products only. So, whichever is more stable product, that will be formed in greater amount. So, here since the reaction temperature is not specified, we will choose the normal product, the more stable product. If temperature was like minus let's say minus 70 degrees Celsius or minus 40 degrees Celsius, then we will be picking this option as the correct answer, because this is easy to form due to greater fraction of positive charge. Okay, so that is the thermodynamic versus kinetic product of conjugate addition reactions. Major product in the following reaction is, this is oxymercuration demercuration reaction. Okay, you know that there is no rearrangement occurring in this reaction. Actually, if you remember, this is the same question as we have solved previously in the, yes, in this case. This is the same question, right? This is the question. Yes. Same compound, same conditions. Just that in this case they are asking for the product structure. In the previous case they are asking for the terminologies, mark or anti-mark, right? So now the difference, same things are asked in different ways. So now applying mercuric acetate, you know, cyclic mercurinium intermediate is formed, and cyclic mercurinium intermediate is then attacked by H2O in this fashion. H2 attacks on this carbon, not on that carbon, and H2 attacks on this carbon, and the ring opens, and we get OH here, Hg plus there, and on demercuration, NaBH4, we get OH and H. Right. No rearrangement. No rearrangement because of the locked intermediate, cyclic intermediate. No carbocation explicitly is formed. And this happens, this is effectively a Markovnikov addition of Ha2O without any rearrangement. If we do hydroboration oxidation, ultimately we will see OH there, H here. That is only difference, there also no rearrangement. Yes, so the option will identify option 1 is the correct choice. Okay, here OH comes, there H goes. Yes. Let's do one question also. One more question. OCH3, and this is also from previous questions. All are from the same previous questions, last 10 years or 11 years. Okay, here HCl is added. What is the major product? That is the question. And you see, on adding H plus, first you know H plus from HCl adds on this or that carbon. We need to identify the more stable carbocation, right? Either this or the other way. Both way is hypothetically possible, which is actually occurring in major amount, is decided by the stability of carbocation, right? The stability of carbocation is greater in this case, more stable. This is more stable, and this is very strong, minus I minus R group, right? And therefore this is very strong electron withdrawing group. Therefore this is less stable. So we can say this is formed in greater amounts, and then Cl minus attacks on that carbon, and we see Cl over there in the major product. Yes, so that happens, and so that is the final one, and all were addition reactions of alkenes and alkynes. Alkynes we saw rarely. Alkynes questions are very rare in your previous questions, and the two main reactions we had discussed, that is one hydration of alkynes giving aldehyde or ketone, ketone mainly, and then HX addition, 2HX addition we can do, and it will give us a geminal dihalide. So the 9 reactions of alkenes also you keep in mind. So you know that most of the reactions are mechanism based, and you should see wherever rearrangements are possible, where it is not possible. You know the basics of all these reactions. Okay, this was one of the important category and one of the simplest category also, but frequently asked type questions, type reactions. So hope you understood, or you could brush up your memories once again and try to apply it in more problems that you practice. I am sure that you will find similar reactions in much more questions, just that there will be another reactions also present in the same question. Okay, that's it. Hope you understood it well. Thank you all.